¿Listo? Ok. Bueno, pues vamos comenzando. Bienvenidos al segundo streaming de la comunidad de Embedded Systems Geeks. Estamos muy contentos de que estén aquí con nosotros por última vez en el año. Este es el último evento al público que tiene Hacker Garage después de que logramos abrir o reabrir este proyecto, el Garage 5.0, así que pues es un poco una celebración en este último evento del año, pero también es un agradecimiento para todos quienes nos ven en casa en la transmisión y a quienes han estado aquí en los eventos con nosotros durante todo este año. Ha sido un esfuerzo en conjunto, ha sido un esfuerzo de toda la comunidad, les agradecemos muchísimo y la idea es que para el siguiente año el Hacker retome actividades full time, entonces esta primera parte fue como de un restart, de acomodarnos, de saber hacia dónde íbamos a ir, pero creo que a este punto ya tenemos un poco más de idea, entonces pues de nuevo les agradecemos, les damos la bienvenida. El Hacker siempre está abierto, es un lugar de comunidad, es un lugar de creación. Vengan, usen el espacio, está todo lo que tenemos aquí, las máquinas, las herramientas, las personas, la comunidad está hecha para todos nosotros, entonces pues bienvenidos y nada, los dejamos con Frank en esta charla de Vintage Gaming, creo que está muy interesante, viene Pepe, está Frank otra vez. Y now I'm switching to English, so welcome Frank this is the last session. This is the last session of the Embedded System Geek community, so welcome and thank you all.
Thank you very much, Cynthia.
Of the year, of course.
Really appreciate that. And just to switch again to English, first of all, I want to thank very much Cynthia for hosting us probably the last 5 months. So we had a lot of very interesting meetings here, and just ignore the dogs. They just like to be around. And also I would like to thank Israel for doing the recordings. If you at any point like to have a recording yourself, Israel, I'm sure, is very approachable and he's doing this as a profession. So make use of those guys as well, because they're also doing an amazing job. So ESG has been going for a couple of months now. I think this is either the 5th or the 6th social. I need to think about it. And we had some really interesting talks all this time that we've been going. Some talks were given by the community, some were given by me, some were given by Pepe, who's also going to talk today. And this social is a little bit different. So we're going to talk about something which is technical, but also which is fun. And we have some games set up here, so we're going to play some games here, but we also want to learn a little bit about how games are developed, what are the technologies that we have used in the past, what is the technology we're going to use in the future for games development and emulation. Not so much development, but really reviving the past to bring back those old vintage games, make sure they don't get lost. So I'm going to tell you a little bit about vintage gaming. And by vintage, I mean not in the nice last 5 or 10 years, but in the last 20 years, maybe 20 years ago, in the 80s. And I'm using an example which I really liked as a kid. I was very bad at it, and I never got beyond level 2 or 3, I think. But it's the game Donkey Kong. And it's a nice little example to show you how different technologies are used to emulate and recreate this game, and what was actually the original technology that has been used when in the 80s, early 80s, mid 80s, these games were sort of being displayed in the arcades and so on. So I hope you enjoy the talk. We will have a few questions. And as I said, feel free to join our group. We are meeting every month. We are trying to collaborate on things, and we're teaching things to each other. We are not all experts. Actually, I'm not an expert either. So that's not a prerequisite to join the group to be an expert. So it's a bit about myself. So I'm an independent consultant. I work currently mostly with industry. I used to work in academia. My special area is safety and security. So I'm working on rigorous engineering of systems. I'm very interested in mathematical foundations as well. So I've published a lot of paper on mathematical approaches to software. And rigorous engineering is also something where hardware comes often in, because when you have a hardware system, of course, you want to make sure it's free of possible attacks and threats. And it's a big issue at the moment as well. So if you're interested, I'll put a link to my publications there, but this is a little bit unrelated. And I'm now living in Guadalajara with my wife. I'm now kind of trying to do different things here as well with communities. So this is the topic for today. We are going to look at Donkey Kong in 3 ways. So 3 kinds of meals, 3 kinds of dishes. So we're going to look at the authentic hardware, which is what you would have seen in the 80s when you played the system, going to the arcade. And we actually have one of those. Pepe also brought one system, not quite as big as that, which we can use. We're going to look at software emulation, which is a software-based technique to revive the hardware purely in software. We're also going to look at some more recent technologies to use FPGA-based, which means field programmable gate arrays, to recreate this game in a better way. And don't worry, I'm not going to kill you at the end. So there's a bit of a menu for you, and I'm spend a little bit of time on all these things and also tell you a bit more about retro gaming. So we're going to look at these 3 different technologies: authentic, original hardware, original PCBs, vintage chips and components, software emulation, and this is the MAME system, or MAME, I'm not sure how to pronounce this, is the system I will look at. And then we look at hardware replication using MiSTer, and there's a couple of systems in the same domain that support this kind of technology. And this will also give you an appreciation of the progress that has been made. When I was a student, a system like the MiSTer would have been way too expensive, even though it's fun to play with. So the only opportunity you have is to study computer science at the university and sign up for a special course on it. Nowadays, you order it on Alibaba, what's the name of the, well, eBay or Amazon. It's very easy to get these. And if some of you want to build yourself a MiSTer device, we are here to help you. We can advise you also what components you need, how to do it. It's not rocket science. It's actually quite straightforward. You don't need to solder anything. You just need to have, well, a little bit of money because these things are not cheap. And this is really the cutting edge technology at the moment when it comes to game simulation. So Donkey Kong, I hope I don't have to explain this, but this is kind of how it looks like. It's a jump and run game. And it was the first occurrence of Mario, I think. And it was actually called not Mario then. I think they called it Jumpman. But it was developed in the early 80s, as far as I understood, by Shigeru Miyamoto. I'm probably not pronouncing that correct. And this was, as far as I understood, a little bit of a backup plan, because they released the console Radar, I think it was called Radarscope, and that wasn't very successful, so I wanted to repurpose the hardware. I thought, what can we do with this? And they had these units produced. It was a small company at the time. I mean, Nintendo, well, nowadays is probably the most, well, best-known company, but they certainly struck gold with that one. I think that was really successful. And this already tells you something about games, that the way that consoles are built is actually not that different, at least in this time. So we usually have sprites that move around. We have some background, which is static. And this is really determined by how the hardware worked at the time. And we look a bit more deeply into this at some point in the talk, but was actually easy to repurpose this game, because when you have like shoot 'em up games or platformers, they always follow like a scheme where you can apply this kind of pattern to it. So let's go to the next slide. So when we talk about early games, there were actually many constraints that engineers had to contend with. So chips were very expensive, especially memory. So they tried to keep costs of memory down, which also sometimes need that these devices don't actually have a graphics memory. So there's no special memory that keeps all your pixels and all your screen at the time, which we call a frame buffer. So instead, the CPU sometimes even had to take the job of drawing the graphics. And the old Atari system, which I'm going to have on the next slide, actually used that techniques. And this, of course, draws computational resources, which means that sometimes you don't have all the computational resources available for your game logic. So the game logic cannot be super difficult and complex to carry out, like we have it in some of our modern games. So there were a lot of kind of trade-offs, and I find Pong very interesting because there were consoles which were hybrid. So a lot of it was analog, not even digital components, mostly analog components. And they're kind of mixing in digital components, and you have these huge circuit boards. But I say a bit more this on the next slides. Atari 26. So I'm saying a bit because Pepe is going to give the next talk, and he might not go that much back into time, or maybe he will, I don't know. We had 128 bytes of memory. Now, how much is that? Very little. It's a string, basically. You can spell your name, maybe your address as well. So it's very little memory. Games had to fit into 4 kilobytes of memory. Later on, they extended that by using bank switching and the cartridges. But initially, it was 4K of memory, where a lot of games were written for. No frame buffer. The CPU was basically feeding the video chip when the beam crosses. And I have a little book for you, which someone brought along, and I will mention this as well within the talk. And this is a very interesting book. It's called Racing the Beam. And to understand the title, you need to see how games were developed at this time, because I really had to race the beam. The CPU had to keep up with the beam in order not to cause any flicker or to make the game look smooth and nice. So this was a very common technique. And that means you need to very deeply understand your processor and know the timing of every instruction, how long does it take, how far you're going to progress with your beam. Are you still in your vertical blank periods where you don't see what actually is happening on the screen? And so it's a very... But surely we didn't have GPUs, and even DMA was kind of rare. It existed, but not in the form we have it like in modern microcontrollers. Atari, 2 player sprites, 2 pixel missile sprites. And that's all they thought they needed to have certain games like, I think there was a motivation that you can implement a game, I'm not sure what the name of the game was, but you have 2 figures shooting at each other. I think it was called Command or something like that. And that was the only constraint. And they thought, as long as we can do that, it's cool. And still developers managed to create some really cool games. So here's one. That was my favorite at the time. Pitfall. And there's a very interesting talk where they explain all the details, how difficult it was to cramp this game. And there's a book, by the way, that I just showed you. So I can recommend that. I haven't read it, but I heard it's good, at least from one person. So it's a very interesting game because they didn't have space on the cartridge to model all of the levels, so they need to use some randomized, well, it's not really randomized, it's more like procedurally generated levels, and there are some elements there of randomness, and they need to go back and forth. So it was there's a really interesting talk from the designer about these games. And if we do even go back a bit, this is how an early Pong game looked like. And you probably need a magnifying glass to see that, and I will make those slides available. I'm hopefully not infringing on any copyrights here. But what you see here is not all digital. You have things here. Let me see if I can find some of them. Well, there's a lot of digital stuff I can see now. But what usually these games have is circuits for operation amplifiers. And op-amps are kind of, a kind of tool that analog tech engineers use. And they can do different things: addition, multiplication, differentiation, integration. They use a mixture of analog signals to driving these op-amps, maybe as comparators, and then they generate the right signals. You see that some of these blocks correspond, for instance, to generate sync signals for a video output. And in video output, you need to have, of course, your color, your pixel information, but you also need to have sync pulses that tell basically the TV when the electron beam goes back, how long the screen is. And so all of this is done kind of in an sort of analog way. I find this really exciting because also it's very kind of difficult to tune these systems. You have probably 50 or 20 different resistors that you need to adjust just to get the right kind of screen. So it's not a very robust technology as we're used to. So let's return to Donkey Kong. Donkey Kong, how did these games actually be realized? What we had is two main techniques, I think, at the time. One is for the background, we have a tile-based approach. And for moving objects, we have hardware sprites. That means the CPU doesn't actually have to draw the pixels onto the screen. All it has to do here is to tell the hardware what sprite is it, where do you find it in memory, what are the coordinates of the sprite. And that really reduces the amount of data that needs to be shifted. So your hardware takes care of drawing your screen. But the CPU really just has to work out the coordinates and the types of images that you have. And usually you have kind of sprite maps and tile maps somewhere in memory. And that is how these things are read. The CPUs were usually not very fast. So I think the Z80 that is used could be clocked to 4 megahertz. That is really, really slow by nowadays systems. I mean, if you think you have cores now in the range of a gigahertz, that's 1,000 times slower, and you just have a single one. So usually you didn't have dual core CPUs. The hardware sometimes allowed you to displace the background a little bit, maybe 1 or 2 pixels, to realize things like scrolling. So this allows you to do side scrollers, for instance. And you can imagine the hardware is not super complex to do that, but it needs to give you just the right amount of features. Consoles used to be able to do that. For instance, the C64 had also, or the Amiga, there were bits to make these kind of pixel displacements. And in the end, you get the illusion that you have a scrolling background which never ends, but really you're just shifting the screen and you're filling up one row when you need to, either from the bottom or from the right. And this is one of the approaches that was used. So course number 1, vintage. This is, I digged out the original PCB of Donkey Kong. I'm not sure if it's Donkey Kong Jr. or Donkey Kong, but I think it's the one that I'm explaining. I tried to find a little bit more out about the components, but it's very difficult. And the image is not very good to actually read the descriptions on the chips. So my suspicion, and I'm not saying it is the case, but I think that one of these must be the CPU, probably. And I also know that this board had a DMA coprocessor. So I suppose maybe this is a CPU and this is a DMA coprocessor. It would make sense to put them close to each other. We have some EEPROMs for the code and for the graphics data. And what these are, I have no idea. I suppose there could be RAM banks. There could be some hardware sprite logic. And when I mentioned that these boards needed to have hardware sprites, that really translates into having some hardware that generates your sprites on the screen. And it's very interesting to analyze these circuits. And there are people who have done this and still doing it to port these old boards into modern systems. And basically what you're doing is you're looking at all the connections that you find between these components, and you're making a schematic out of it. And once you have the schematic, you can start to extract the data and the software and create and simulate it, which I'm going to talk a bit about later. But this is how these boards look like. When you open an old cabinet, you find a board like this. There's also some high power kind of circuitry to deal with the CRT. But this is basically the heart of the game. So this game, Donkey Kong, was implemented on the Z80 processor, which was very popular in the 80s. It's an 8-bit processor. It also made use of a DMA coprocessor. Why DMA coprocessor? Well, these processors are quick at shifting data. A CPU usually needs a certain number of cycles to shift a single byte in memory. And because these were 8-bit processors, I mean, it will take very long. A DMA coprocessor is a bit like a state machine. It's a simple state machine that you can tell it, here's the start address, here's the end address, now copy the data. Now, I know there's more complicated DMA coprocessors, and if you look at the Amiga, it had kind of, I think, several processors that used DMA. And they were specialized for sound, for graphics, they could draw lines, they can fill areas and things like that. So this is a very common technique. Of course, it also has some downsides in the fact that the bus where you do your memory access could be a bottleneck, which is, by the way, why the Amiga had two kinds of memory areas. It had chip mem, which is used by a DME, and then it had something called fast mem, which can be used by the CPU. But that tells you also about the challenges of designing games and racing the beam, as I said. So sometimes the boards are also engineered to generate analog output signals. I'm not sure what the format is, but I suppose it's some kind of composite or component video, something like PAL or SECAM or NTSC or VGA in the same kind of domain. And there are a lot of folks who reverse engineer these things and publish them. And if you look at the right sources, you actually find things like that. So authentic hardware. The pros are you have really the feeling, yeah? Scan lines, and I mean, it's very hipster, very vintage to have like a thing like that. If your partner allows you, that you're taking a lot of space for it, or maybe you have a cellar. The downside of course, these systems need maintenance. They have their bugs and quirks, and they degrade. There are certain components that do degrade quite badly over time, mostly capacitors. I mean, for these systems might not be so bad, but even chips over time, you might need to replace them. And you need to know a little bit about how to maintain these systems. I think just having one and then paying hundreds of dollars to maintain it is maybe not the best option. They take up space. You can't save and restart the game easily. I mean, if you want to train yourself in certain levels, that's difficult with these systems. And they're not cheap nowadays. So this PCB, I think you can probably find it for about maybe $300 to $400, maybe more. I'm not sure. I think a well-preserved one will probably cost you more than $500 to buy. I'm not sure, but these, I know that they're not cheap. So we looked a little bit at the old system now, and I don't want to get much deeper into it. Let's go to the next stage, course 2, emulation. So how do we play games nowadays? I mean, we don't have this hardware available. So what we're doing is basically we are creating a software emulation on a machine that's powerful enough to, at least at the logic level, simulate the game sufficiently well so that we can play it and we don't see the difference. That's always the motivation. To do this, you need a very deep understanding of the hardware if you want to do it well. And it's not just enough to extract the code. You really need also to know the timing of the system. What's the clock rates, what are the delays. Most of the time, if there's just a few cycles delays, you wouldn't see it. But of course, we're perfectionists and we want to do it exactly, precisely. We want to really understand how it works. So the circuits are usually not emulated at the gate or physical level, but at the logic level. What does it mean? If you decap a chip, you can, in principle, completely reconstruct all the wires and all the gates and switches that you have inside it. Now, we don't usually want to do that because, or at least it's difficult to do that. What we want to have basically is just a logical simulation which captures the essence of how the chip behaves when you have some signals, some instructions that you're going to execute. And that is also much faster to simulate. There's some people who have done that. They have done physical level simulation. Gate level simulation is possible, but that's not used for game playing. It's too slow. You use it for validation. If you develop a new system, sometimes that's useful, but not when you want to play a game and not wait half an hour before the screen moves. So emulations are not always entirely accurate. They try to be, but there's always like things where you have some gray area, and most of the time you don't know this. Sound is an issue. I mean, to simulate a sound device accurately also takes computational time. So sometimes you resolve to using samples for this. And you wouldn't see the difference really, but it's not quite the real thing. It's a matter of, is it worth to spend your CPU time doing it? And reality is we just don't want to see the difference. I mean, as long as it's good enough, we are happy. So this is a very interesting part, time. Because emulation is all about time. And if you don't get your time control right, the game will not be playable. So what are the problems? Simulated time is not the same as real time. So we have a simulation which can be super accurate, but it takes a year to run in some ways. And you know, what we want is a response quicker. The OS might sometimes stall our process. It could say, well, I need to read some data, there's something urgent to do, so I'm going to stall you for a while. Usually you don't notice that because it might just be for maybe less than a millisecond, but it does happen. And the other issue is that modern processors are 2 to 3 orders of magnitude faster, I think. So you will actually end up your simulation going, in some cases, way too fast. If you run it at full speed, you're not going to be able to play the game, which is finished in a second, and you're dead. You don't know why, but that is how it works. So let's assume our simulation moves in 20 milliseconds, and that's about the size of a 50 hertz frame that it takes. And I'm putting the real time here, just to show you. Now, the simulation time is at the bottom, and we might, in less than 20 milliseconds, already have finished the simulation of a particular frame. That means we need to wait. And at that point, we need to sync again with real time. So we cannot basically just run our simulation as fast as we can and just continue. There are points of observation where we have to show the new screen, where we have to refresh the screen, where we have to take input from the user. And these are always usually taken here when we reach the end of a frame, which is about 20 milliseconds. So to manage this, it means we're going to run as fast as we can, like the rabbit, and then we're just going to wait. So the time in our simulation gets squeezed a little bit. And we have this point of synchronization here where we just wait, and we go in lockstep again to simulate it in real time. That is usually how MAME and other simulators work. There could also be situations where we might even overrun time. So here, we haven't managed to do the simulation within a frame. So we overrun it, and then we can just hope that in the next frame we're going to catch up and nobody notices it. So these are the complications that you are facing, because even with most operating systems, they're not real-time kernels, they're not real-time operating systems. So at that point, we cannot make strong assumptions about the resources that we will have in terms of timing. Microcontrollers are a bit better. If you do this on a microcontroller, and you do it bare metal, you can make these strong assumptions. And you're not going to run into these issues. But you might even then still have the issue that your microcontroller is running too fast. Because even nowadays, microcontrollers are 10 times, maybe even 20, 30 times faster than this. So here the simulation runs ahead, and here the simulation lags behind. But the issue is always that we are trying to catch up with the simulation. Oh, thanks. I should use the pointer as well. I think that's very, very useful. Yes. So here it lags behind. And just to explain this paradigm, what we want to do is we want to go in lockstep with real time. As I said, 20 milliseconds is a refresh rate of 50 hertz, and every 20 milliseconds we make an observation. And when we are in simulation mode, like the rabbit, we're going to run as fast as we can. Once we simulated a frame, we're going to idle until the real time has caught up with us. And if you overrun time, you're just going to hope that in the next frame, we are going to catch up again with the simulation. So MAME is a system which has been developed to do exactly that. And about 4 years ago, I had a bit more time. I got really excited about porting Donkey Kong to a different platform. So I looked at the MAME system and tried to understand this. And my state of knowledge that I'm telling you is basically 4 years ago. It might have changed since then, but it is, I think, most of the basics haven't changed. So MAME this is the main statement of the project. The purpose is to preserve decades of software history. As electronic technology continues to rush forward, MAME prevents this important vintage software from being lost and forgotten. A bit like Indiana Jones. It belongs in a museum, kind of thing. And it's also saying the fact that the software is usable serves primarily to validate the accuracy of the documentation. So it's not for playing games. Of course, this is a bit tongue-in-cheek. And I think they're just saying this a little bit also to say, well, we are not just a pirate project, you know, we want to rip all the ROMs. But there's a really, when you look at this project, a lot of people take a lot of painstaking effort to build very accurate reproductions of CPUs in software with precise timing, which gives you also the bus, the interconnects, everything they try to basically model in the system. The documentation is essentially the code, and if you're not happy to read C++ code, it's maybe not a good place to start, but it's reasonably well developed and designed. It has been going for a long time. And Mame is now, I think, has been merged with another project and now documents a wide variety of mostly vintage computers, video game consoles, calculators, arcade games, when arcade games were actually the initial focus of Mame. So it's definitely, if you're interested in vintage gaming, you want to write something, don't do it from scratch, use a system like that. Maybe try to understand it, and it already has a lot of ready-made components for you. So I think, in a nutshell, it's the most comprehensive arcade and console emulation framework at the moment. It's a de facto standard for, you know, recording the precise behavior of things. It can simulate down to attoseconds with, I think, 96-bit precision. Most of the time we don't use that because we don't need such an accuracy. But if you have the very subtle timing of hardware devices that run at high frequencies, even if you want to consider timing between wires, I mean, sometimes there were bugs in chips where they produced timing discrepancies in wires. For instance, the C64 sometimes needed to sync with the raster beam and the start of the beam. And you have a lot of complications because you have things like bad lines and you don't know when the hardware. So this synchronization, I don't know if this is related to this, but this is the kind of thing that you can model with attoseconds, really. It uses external C++ libraries. It's quite a beast. So if you're not used to working with large code bases, it's not easy to get a start with. If you're used to do that, you should find your way around it in some ways. And I studied, as I said, this is part of a pet project to convert Donkey Kong to a Raspberry Pico. And what I wanted to do is just extract the code I needed, because I don't want to have all the other stuff. And I managed to do that. I want to show it to you today, but yesterday I compiled it, didn't work on my Mac because SDL crashes. Sorry about that. I might show it to you later, but maybe next time I will make this available on GitHub as well. And if anybody wants to engage with that, we can do it together. I'm almost done with extracting the code. It runs, but I need to convert the assembler. And the assembler uses lookup tables which are too big for Pico. So I need to change some of that lookup table speed up by doing some computations, but it still should be fast enough. So it comes with a large set of reusable components. I'm talking a bit about the anatomy of the system. We have different CPUs in there. We have different chips. And the CPUs are usually not the problem in emulation. You have libraries that already have CPUs. But things like the Commodore VIC or SID chip for the sound or the graphics or the Atari TIA, this is where the engineering becomes tricky. Because most of the time, the difficulty with new systems is that you don't understand the special chips they have. And you need to use something like a logic analyzer, or you need to use all documents. Sometimes you just need to talk to people, because these things get lost to figure out how these chips work. You have sometimes some auxiliary chips, they're also represented. And when you emulate a new game, first you try to find some existing components and connect them up. You don't want to reinvent the wheel, and that's the advantage of using a system like that. If there's anything exotic which you don't have, you have to grasp the nettle and actually try to understand what it does, build a simulation of it. And the difficulty with these frameworks is usually that they're very complex. So you need to connect things up, you need to use all the existing classes. For Donkey Kong, it's about 3,000 lines of code to do that. So it's not a walk in the park, and this is a comparably simple game, but it's just organic how these frameworks have basically grown. And that makes it quite complicated. So it's a few statistics. It's been started, I think, 1997. There's quite a few releases, almost 500 contributors. And here's a bit of source code you might find interesting. So this is a directory where you find the Donkey Kong setup and sources, and it uses the Z80 CPU, so this is in a different directory. You find the Z80 CPU emulation, and most of it, as I said, is C++. There's a bit of C, a bit of Python and Scala even, and Lua, but most of it is C. It's open source, it's 3-clause BSD. I think it runs on another license as well, but it's all open source. So you can be sure whatever you're going to do there, you're going to contribute to it. And I'm just going to see if I can show you a little bit of the code. I don't want to go too deep into it, and I think my mouse has just stopped. Ah, no, I can still see it here. I just maybe have to move it a bit slower. Ah, I cannot see it. That's a bit strange. Ah, yes, I can see it here. So this is the Mame project on GitHub, and I've already opened some of the code here, which is probably a bit small for you to see. Let's see if I can make it a bit bigger. And what you can see is when you read the code that there's a lot of comments and information. And this is exactly the information that you need in terms of developing the game. They tell you something about memory layouts, they tell you about hardware, switches, add-ons, revisions, things that have been put on to the board, because this is not just emulating a single game, it's a whole family of games that came out of this board. And this is useful to read through. For instance, this is a memory map. You learn something about sprites, something about ports, and eventually you get to the code, and the code uses a lot of sort of internal stuff from Mame. So if I go a bit further down, you find a lot of preprocessor statements here related to the layout of memory. So you have these are actually functions, but you also have different kind of inbuilt kind of preprocessor statements to set up the system. And the reason you need this complicated setup is really that you can have save states and that the system is very deeply aware of the system you're building, so that you can save this anytime, the hardware, the state of the hardware, and so on. And it's, as I said, it's not a walk in the park, but it's still interesting when you want to port something. Rather than doing it from scratch, I would probably look first here and then see how much this makes sense. It gives you a lot of information. Here, we actually have the code for the assembler. And this is a model of the CPU that you're simulating. And again, it's a lot of code. And CPUs usually work with a massive case statement. So somewhere in your CPU emulation, you have a massive case statement that goes through all the different opcodes that the CPU has. You're working also with lookup tables for your flags. And usually these simulators are not rocket science to write. It's a nice student project. If you are studying computer science, you want to build this, and it's a lot of boilerplate, but you see there's a lot of small functions here which implement certain kinds of functionality, for instance, outputting some data on a port. And a lot of times these operations also need to set flags and so on. It's fairly straightforward, it's just a lot of fiddly work to actually implement that. So just that's as much as I want to probably tell you about Mame. I found it useful when I looked at it, but this is not yet the bee's knees. So let's get to the bee's knees. Course number 3. The third course should always be the best one, right? I mean, when you go to a restaurant, you want to have a nice dessert, right? So this is, Mame is the main course, I guess, and the other was a bit the starter, and now we're going to the dessert. So I need to explain a little bit about simulation and replication. When we talk about simulation, we needed to think about time in 2 different ways. Time, which we cannot see, that runs in the simulation and is kept meticulously track of, and the time that we are observing from the outside, which I call real time, so the actual time that passes. And as I said, these 2 times can be different. I mean, if you've seen like the Inception, they play a lot of with time and how time can move slower and faster, and this is exactly the problems. That means because our computers cannot afford to wait, they need to run like rabbits when they do simulation, but then they have also idle times. So it's basically always try to be ahead so you're not going to fall behind. That's basically the way that simulation works. Replication is very different. replication really tries to execute the CPU in the actual time that it took in a real system. So it's not building a simulation model, it's building a hardware model that is clocked by a quartz or by some PLL or whichever you have. And it runs exactly at the same time as the original hardware. And it cannot be slowed down because it is not connected to an operating system. You need to think more of it as a separate piece of hardware. A kind of Frankenstein zombie of your original CPU, basically, but which is close enough so that it does exactly the same thing. So as I said, this is what we do in a simulation, but this is on the premise that we cannot tell the difference, of course. So we are assuming that our computer is so fast that these little issues where we would see a difference don't occur. So what if I told you if there's a way we can provide a real-time simulation of every chip, every component in real time, in the same timing, and we're almost recreating the whole system within. So this is not a new technology to do that. This has been available for quite considerable time. It's called FPGA, Field Programmable Gate Array. When engineers develop hardware, initially, well, we don't do that anymore. Well, we still do it sort of at the bottom level, but we have languages to do this as well. They're writing circuits, digital circuits. Now, an FPGA can natively execute such a circuit. And you can think it as a tabula rasa, as a construction kit. So I think maybe some might be old enough to know Cosmos. I had a Cosmos kit, which was the I think 200. You can make radios with this, and you plug the components together. And this is a little bit the same. So you can plug your control logic together, and then you can program the device through lookup tables. So it will have lookup tables which can execute any logical functions. And then you tell us, no, I want you to execute this logical function, a half adder. And the tools basically work out how to configure that logic. Circuits run in a sense in parallel, which means you're not slowed down and you can do a lot of things at the same time, a lot of specialized tasks. And the circuit is not hand-wired, as I said, it's specified in software. But once you translate it to the device, it actually runs like a real circuit, essentially. You don't see the difference. It doesn't quite run as fast as a CPU, a modern CPU. You're thinking the fastest you probably get out of an FPGA, I don't know if it's a high power one, maybe in the range of 500 megahertz, I think. But I'm not sure where the state of the art is. But of the COTS FPGAs, they, maybe 100, 200 megahertz, depending on the circuit. Because the circuit itself will have some delay and there's some timing constraints you need to meet, like setup and hold times and things like that. So this is the technology. The project that recreates games, the MISTER project that I will mention on the next slide, uses this kind of board. So you have an FPGA in the middle, and this is actually not just an FPGA, it's also a processor system. And they call this a system on chip. So it's a bit like a microcontroller, a modern microcontroller. You don't just have an FPGA, you have also a dual core ARM processor there, I think. You have some additional hardware around here, you have some memory. I think this is a HDMI display coprocessor. There's another FPGA which is used for probably for USB and other connections. And so these boards usually come with a little bit of bells and whistles that you can use to implement it. And this is kind of, I would say, it's not the cheapest one, but it's not a high-priced one. And if anyone wants to build themselves a system like this, which I'm going to show a bit later, which is built on this FPGA, it's called a MISTER, need to get yourself one of these boards as well. Unfortunately, they have become quite pricey. They used to be cheap. I think as a student, you can get one for $140. Now you probably have to fork out a little bit more for it. I think it's about $240. They trade now. Import duties in Mexico also cost a bit. So it's not the cheapest thing to use. The name of this is a D10 Nano. And this FPGA is a Cyclone 5. It's reasonably powerful. It's not the latest, I guess, but it's still it's a working horse for this kind of systems. So the MISTER project was started, I think, in 2017. So it's not as old as a MAME project. By a guy which goes under the name Zorgelik, and you find them a lot on these posts and forums and in the software development kind of GitHub pages. It's community driven, and all of this is open source. So this is completely, you can contribute to it, you can see the whole of the models, everything is available. The only thing that's not available open source is of course the board itself, but all the add-ons that you have, all the daughter boards, that's all open source. So it has vintage arcade machines, it has gaming consoles, it has home computers, and there's really a big list. I think there's about 50 different home computers. There's another 30 or maybe 40, I haven't looked how much they have now, gaming consoles. They support also more modern systems. I think things like, I think the Sega CD was there, the Genesis, I'm not sure. But they are trying to push the limits of the device. And there are limits. You cannot, you can't have a PlayStation 5 running on it because it's just not fast enough. You don't know the technology. But everything that maybe goes to 5th generation shouldn't be a problem at all, and you can even go beyond that. So 16-bit, 32 bits, I think it's definitely feasible. So the community also develops the add-on boards, and it's a very different technology. So the cores are implemented in Verilog VHDL. So those who know a little bit about hardware design uses special languages. These are not programming languages in the way we understand them. And you really need a different way to think about these designs. Your main things are basically registers and wires and combinatorial operations between them. And you can use a programming like languages to specify them, but it's kind of a different way of thinking how the code executes. One thing is that things are not sequential. They're parallel by default. You want something sequential, that's where the work goes. With usual program, it's the other way around. Sequentiality is the default notion, and if you want to have something parallel, you need to use some library, or you need to be careful with this and use some tricks as well. So this is how the MiSTer looks like. In the middle, you have sandwiched the FPGA board. You have on top of it another board which gives you a VGA output, but this also provides HDMI. So if you're happy with HDMI, you might not even need that board. But this also has a fan, which is important because these FPGAs tend to get very hot, especially if you run a lot of logic on them. And you have a USB expansion board on the bottom. And you get this also in different versions. There's a high, low latency, high speed version of it. And there's also a little memory module that you need on the back, which is a fast memory that the system uses. Otherwise, there's just an SD slot somewhere. And as I said, all of this will cost you about maybe $400, maybe a bit less if you build it yourself. There are suppliers for that. You don't need to make the boards yourself. You can if you want to. The schematics and the information is available. But you can just order them from somewhere. So this is the USB board. This is the expansion for the VGA and the output. You get this with digital and analog output. You also need a memory, one of the memories. They come in different sizes. And there's a few other things which are not essential, like you have a real-time clock if you want that one. You can also add this if you want to have a fancy thing. But that is how, and you assemble it, and then you buy yourself a nice case. There are some nice, ready-made cases for that. And if you need some advice, I can also point you to some high-quality suppliers for that. And they're not cheap, but so the MiSTer development, as I said, just to understand a little bit better how this works. And I will just go back to the slide I had before. It requires a shift in understanding. And Sia is here, he runs the Kotlin group, and we talk a lot about functional programming. And sometimes people find it difficult to think functionally about programs because it's like different from what we learn sometimes in university or when we teach ourselves. And hardware engineering for me is kind of the same. It's the same amount of effort, mental effort and shift it requires. I've already mentioned that we need to understand that we need to go from sequential to parallel. We need to we we need to understand the hardware that we're modeling. So you cannot build a model of anything without understanding the hardware. And in hardware engineering, this is even more so. In software engineering, you can get away not knowing exactly what you do. Hardware engineering will give you a lot of pain because you will get bugs and issues, you got timing problems, and I follow the guy who develops a lot of this stuff. And it's very interesting when he comes up with new ideas and tells the problems he's having. He has a Patreon page, and you can also sponsor this guy. It's called Hotego, and he does a lot of these courses, and I think he's doing a really great job with that. Detectives. You need to be a detective in reverse engineering, and people will know what that means here because he's using logic analyzers all the time, and it's sometimes very difficult to find out the nitty-gritty. So chips are not always like code. Chips have bugs. They have sometimes behaviors which are not in the specification, which we cannot really understand. And the problem is we need to understand the bugs to implement the games, because we need to even reproduce the bugs in the chips sometimes to have an accurate simulation. Or we need to at least understand them enough how they impinge on our system. The tools we're using are very different. We're using synthesis tools and verification tools, which take our Verilog and high-level languages and put them down into a format that basically boards like this understands, and it's still binary. So don't worry, it's still binary, but it has a completely different meaning. It's not a machine code, it's called a bit stream, and it basically is an encoding of the circuit that we're going to put onto the device. Simulation is also necessary because sometimes it's difficult to debug things. I mean, we do have sometimes logic analyzers, things like JTAG, or we can put an UART interface there. And complex systems usually have some UART port for logging and things like that, but it's not so straightforward. So next year in ESG, we will do a bit more on FPGAs. And I have already planned 1 or 2 talks to get us started with very simple designs. We might even have something which is a bit more sophisticated, generating a video signal. People was asking today if the device is doing the video signal. The question is yes, and actually it's very easy to do that, because the FPGA is so much geared towards this kind of thing, and the timing, you can do it perfect, you get the right timing. It's very easy to have a VGA driver for these kind of systems. So we are almost coming to an end now. So I want to show you very quickly how this code looks like, just so that you get an impression for those that are interested in how we program these devices. And I hope I'm having it open here. So this is the MISTA development page. We have a directory RTL. So RTL is the equivalent of a source directory in GitHub for hardware. So RTL, sorry, I'm in the wrong tab here. Let me just go here if I can magnify it a bit. RTL stands for Register Transfer Logic. And this is basically your source code. And as you can see, we have some files here. Let's look at an easy one. So the Donkey Kong has a DMA chip, a DMA controller. And here we have a description of that DMA controller in a hardware description language. What you can see, it's very concise. It doesn't have a lot. And at the beginning, we have inputs and outputs. So we have a module here, which has some inputs, Boolean signals, and some outputs. And these are the outputs of the chip. So whoever wrote this, he had the actual physical chip and then decided that he needed these inputs and outputs. And some of these can also be arrays of bits. These are just simple wires. And I'm not sure what they mean. They might give us the address. They might give us, so these are control outputs. They're directly connected to the bus to read and write to memory, most likely. And they also need to get access to the bus. So they probably have some sort of protocol to tell the CPU, look, I need the bus. And the way we write a Verilog program is basically to say, every time we have a positive edge on a clock, so a signal changes, we want to execute some kind of process. And then this process updates some of the internal registers. So the equivalent of a variable in Verilog is a register. But you think of a register really just something in hardware. So it's not a register in a computer code. This will be synthesized inside your logic cells. And these logic cells can do combinatorial logic, but also they can have registers. And something, I don't want to go into much detail how this chip works, but it's essentially a state machine. And you will have seen this in software engineering. Those of you who do a bit of architecture engineering, they will know about state machines. And this model actually is not entirely accurate. So the MR guys, as last time I looked at it, they have taken some shortcuts. Because I look at Donkey Kong and I say, I don't need the full functionality of the chip. And this also brings you back to this, is it better or is it more accurate? It is only as accurate as your hardware model. Even in a hardware model, you're taking shortcuts. Here, I'm not reproducing the exact chip, I'm just reproducing the logic and the timing. And the timing is basically what you get from the clock. So you have a clock input, and you have also clock enable and the reset, and this determines the timing of the chip. It's not the role of the chip to generate the clock, but it has to respond to the clock. So you will have an outer framework that generates all the clocks and the clock domains you need, and that kind of determines how that works. So this is a rather simple example, but you have a Z80 emulation will go into thousands of lines if it's accurate. But again, when you get your head around this and you know what these operations are, this is for instance a non-blocking assignment, and that's executed at the end of a cycle, then you also learn how to use these things. And it's a different engineering discipline, but since we are embedded geeks, we want to learn about that as well. So let me just finish the talk. And before I do that, I want to quickly see if I can do a demonstration of the device. So I don't know if we have some power here. I think there's a power, so just excuse me for 1 second. I need my my charger, exactly. Thanks very much. Cheers. We haven't tried this, so if it doesn't work, don't be disappointed. But I just want to see you how it works, just in case you like to build one yourself. So also, I think I need an adapter. I think I have that at the back of the weather white. Yeah, I still need. This is a UK. I think it's the plug in the wall where I have it. Yes, it's a small one. Yes, exactly that one. Thanks very much. We're just preparing. Thank you so much. Yeah. Cool. So we have to plug this one in. And I will just plug in the device now. It needs 2 power supplies, one for the expansion board. And how are we for time? Okay. So I just plug this in. And it works. So what you see right now is the OSD, the on-screen display. And this on-screen display basically doesn't run on the FPGA, it runs on the processor of the system. And that means it's not interfering with any of the FPGA execution and not slowing it down. And this system runs on Linux, so it's not bare metal, but we don't care about that because the actual FPGA cores do run, are not dependent on the Linux. They're completely separate, and their memory system, the memory bus is completely separate from the SOC that runs on the thing. So we have a lot of arcade cores here, and we can maybe just see if we can find one. And I should really find the one that I showed you, which is the Donkey Kong one. And as you can see, there's a lot of stuff here. You can download all of these automatically. There's a script that does that. And sometimes you can also find bundles that I might have passed it. Yeah, I probably have to go a bit further up. Donkey Kong US. And what you also find is that they have different sets of ROMs and bootlegs. So you can play different versions of this game. So you're starting this now. Now the FPGA is initialized. And this initialization basically feeds the FPGA with a bit stream that you need to play the game. And now the game is already running. So if I press coin, and I now need to find the start button. And I might have paused it accidentally. No. Did I pause it? Yeah. Yeah, that was the pause button. This is for the coins. And yeah, it's a bit, sometimes the keyboard, you need to figure out which buttons you press because that can change between the cores. And you will have sound as well, so the device produces sound. We don't see that now. I have to say I'm very bad at playing games nowadays. Reflexes. And you can play the game almost like the original. But I should say here that this, as I said, is not a simulation. It tries to replicate the original as much as possible. So if you want to, for instance, train yourself and you want to practice kind of speed running or... Oh, I'm already dead. See, so it goes very quick. This is a very good way to doing it. And this is an old 8-bit game, but the FPGA is powerful enough also to simulate Neo Geo. You can play Metal Slug. You can play loads of other games. So just to give you a little bit of a flavor how the system looks like, how it works. And there's a lot of things you can also set up. So I can go back to the menu. And I have some things I can change. For instance, I can simulate, I can flip the screen. I can do some adjustments to the hardware as well. I can simulate scan lines to get more of a retro feel. And I mean, as I said, it's not as good as like a real CRT screen or something, but there's a few funny things you can do with this. So I'm just going to go back and wrap up the talk. And I just need to plug my computer in again. And you find a lot of information on this on the web because it has become rather popular within the gaming communities. And there's a lot of people now who build themselves these kind of devices. So I think I need to, yeah, that's great. So as I said, RTL, we looked a little bit at RTL, stands for Register Transfer Logic. And you're thinking of combinational circuits and registers. FPGAs also sometimes have memory and PLLs and other things and fast multipliers and I don't know. There's DSP-like entities as well, but essentially it's just registers and logics. Learning to write ETL is a different paradigm. And as I said, I compare this to functional programming. You will have the same mental struggles to learn it, but once you understand it, it really gives you something new. And it really helps you to develop not just as an engineer, but as a programmer as well in some ways. It opens some new doors for you, which is why I'm very excited. I taught myself FPGAs. I didn't study this at university, and now I'm doing consultancy in it. So if you put your mind to something, you can make leaps as well. Give yourself, start with a simple system first. Don't start to program this, it's too complex, but you get FPGAs for $15. And I think at some point we will do this in ESG as well. Pros. So this is an interesting one. Simulation of all components is timing accurate. I'm not saying that MAME is worse. If you run Donkey Kong on MAME, you wouldn't see a difference because the system is so easy to emulate, and usually operating systems, you have lots of cores. It is not so much of an issue notice. You still get timing accurate, I guess, most of the time at least. But here you really have 100% accuracy. You're not slowed down by the OS. You can exploit parallelism of the FPGA, which means that you can do more with less clocks. If the FPGA cannot be clocked faster than 200 megahertz, you just duplicate whatever you have. And it can still kind of do that. The Consys is not cheap. As I said, $400 for a full system if you build it yourself. It is not always faithful in the sense that it is timing accurate, but not always as faithful as MAME. And there's a kind of religious debate between people who say software emulation, hardware emulation, and people always say, oh, MISTA is better, FPGAs is better. I agree with that in terms of running the game, but the effort of MAME is not about playing games, it's about history, it's about Indiana Jones, you know? We want to reproduce the thing most accurately. And often people also that do this FPGA course, they're taking help, advice from Mama. I mean, they're not there to actually bring out their components and their oscilloscope and logic analyzers doing the work from scratch. So this is a two-sided thing. I mean, there's a lot of effort and development, but it is slow. Slower than doing it in software. And I think anyone working in hardware knows sometimes you have different obstacles in analyzing hardware. And in software you have powerful debuggers, you have different issues. The software issues are usually that software is written in a pretty shitty manner. Not always, but many times it is like this. And the same actually sometimes applies to hardware as well. You can end up with very messy hardware models. It replicates hardware one-to-one, so you're also reproducing glitches. And, well, you can also fix them. I think it's not that it's beyond fixing. But the incisions are more difficult. Save states, for instance, is an issue. Because when you have a hardware system, it's difficult to take a snapshot of it and restart it. So there's a really nice engineering thing. It's called the action replay. And that was popular in the 80s. I think C64 had one. There's also Game Genie, and the Amiga had one. And the interesting engineering is that they needed to kind of reproduce internally what the state of the system is, because they couldn't probe the signals. So they create a copy of the internal state, so when you interrupt the game and you want to rip some music or you want to peek and poke to give you more lives, you need to get back to the hardware. So the hardware thinks nothing happened. It cannot see that you interrupted the game. And it's this is kind of the technology kind of that you need to use sometimes to do that. It's not trivial. And the game library is not as extensive as MAME. So there's a lot of porting efforts, but a lot of this is done open source by people who work, for Intel or other companies, and they're using their knowledge to give something to the community. But of course, they cannot do that, as a job. So conclusion. This was a bit of a tour de force. And my idea was to show different sides. The software side, the hardware side, the electronic side, which I think come very nicely together in this. Is this all just fun and games? I guess to a certain extent it is. But also, simulation is used heavily in industry. In cyber-physical systems, hardware, software, co-design. And there's also standards like the FMI, the Functional Mockup Interface, which actually defines standardized APIs to do simulations. And it's something you find in industry, and it's in what I showed you about this lockstep time progress. You find exactly that if you have hardware in the loop in simulations. And it's not trivial to implement this, and there are research papers written about this in the last 20, 30 years probably, and they're still being written about this, and it's a very active area of research. FPGAs are more accessible these days. You get even low-cost ones for less than $20. So there's no excuse if you like to try it out. You don't need to enroll in a university course. You can try it in your home. There's materials, teaching materials available. These FPGAs are quite powerful, even for the money you pay for them. They're not, of course, industrial scale space technology up to scratch FPGAs, but they are still useful for experimenting. And also some of the tools are open source. There's a lot of stuff now on RISC-V. So if you want to build yourself a RISC-V SoC, you have things like ChipYard that gives you basically all the ingredients you need. There's also other cores like Microblaze and Neos, which have open source versions that you can use if you want to build a SoC. Well, there are tools that are also open source for the synthesis. For instance, Quartus, I think you can use. There's other tools that are open source. And personal projects, I want to convert this Donkey Kong to a Raspberry Pico. This is not FPGA, but still interesting because you need to contend with the memory restrictions of the device. Happy to collaborate. So that will hopefully go into the ESG repository. And I don't know where this image is here. I probably wanted to copy it somewhere, then realized I didn't have space and forgot to remove it. So I should maybe, yeah. It's an Easter egg, not quite, because you're not supposed to find it. Yes, exactly. Or maybe a glitch or something like this. That used to be popular. So this book, I haven't read it myself, but I'm looking forward to, that tells you a bit probably how to develop software in the 70s and 80s. I think it looks nice. I'm looking forward. It got good reviews. That's how much I can tell you. You find MAME, there's some developers information. It's not always complete, but if you're not shying away from reading code, this is a good one. Mista, there are some websites now, and there's loads of videos about Mista now. YouTube, just type in Mista, you find loads of stuff. You can also look at the development sides of it. There's many companies now specializing in components. There's one in the US, in the UK. And there's companies everywhere, also in China. Most of the parts are anywhere produced in China, so it doesn't matter what you order. And these videos here, some of my favorites. There is one about a talk at the German Chaos Computer Club that used to be really popular in the 70s probably. I'm not sure when they started, but definitely in the 80s. And they were always notorious like this ethical, I think there became more ethical hacking and security-aware conferences, but they used to stage always this kind of hacking things to say, well, at this point, security was a non-issue. They just didn't do it. And then there needed to be some people to say, no, you cannot do this. You have a responsibility. Pitfall that I showed before, there's a very nice post-mortem of the developers. You tell you all the things they need to do to squeeze it into 4K and why it is so genius. Elite is a marvel. It's really a masterpiece. I never understood this game, I never liked it, but when I looked at it, getting a bit older, I kind of see it's an open universe trading game that fitted, I think, in a very small, had a very small memory footprint. It had 3D graphics, and this talks a lot about the BBC Micro. And I think it was first actually developed for the BBC Micro, which was a very popular system in the UK. And it was cool because they really had an agenda getting computers into schools. And it was state funded. It was lovely to have the state at this point being aware of the need to get young people into computers. Every school had a BBC Micro. And it was a good system, I think. I don't have one. I might want to get one at some point. And there's also very nice, when I taught you about simulation, someone actually decapped a CPU and took photos of it and build a complete accurate model, not just of the logic, but also of the connections, because this CPU had some weird behaviors that nobody could explain. And games often exploit these behaviors, but it's very difficult. So thanks everyone, especially everyone seeing us on YouTube. Also everyone who came today. I'm really glad we have a small group now, but I understand it's the end of the year. But please, if you see the talk, join us in the ESG group. We will have more interesting talks. As you can see, we take a lot of effort with presentations. We will have a follow-up presentation from Pepe, who's also talking about, I think, Nintendo, the evolution of Nintendo games. And does anyone here have any questions? Yeah. So I think there's a lot of information, and I understand this is something that takes time to digest. I want to just show you these things to see that computing is not a small field, and you should always keep an open mind to things. Because as I said, for me, hardware was almost tasty. I really liked it. When I was a student, I would have loved to do it. I went too quickly into research, and I had to finish my master's, so no time to do it. And then just when I was working as a postdoc, I got interested in hardware. I said, cool, just buy myself an FPGA, and I did some, encoded some simple drivers. Most recently, I've been working on a CPU, which I'm using as examples with my company to show how we properly define product lines. And we are living in a real paradise nowadays. There's so many languages. Even Verilog and VHDL are not anymore used exclusively. So we have very high-level languages which bridge a gap to functional programming. So functional programming is making a resurgence in almost any area now, from software engineering, Kotlin, Scala, to hardware engineering, where we figure out that functional descriptions are just so much easier to use than the low-level hardware, and also safer to use because there's less scope for errors and so on. So thanks very much to everyone. And we'll have another talk in, I guess, half an hour, Pepe? Or we can start maybe in 15 minutes. Cool.